Okay, so let's talk a little bit about the normal curve. What did we know? We know this. Now, what are we saying here? This allows us to compare shoe size to SAT scores to heights of adults. Why? Because now the actual value, the raw score of whatever context you're in, doesn't really matter. Like, I'm glad you got an 82 on your test. But the question is, how did you do relative to the other students, right? That was the idea behind the percentile and the standard score. So what we're measuring here are deviations from the mean. That's what a z-score is. So when we refer to the z-score, we refer to the deviations from the mean. Now, as it turns out in life, lots of data has a symmetric relationship, right? And we've talked about this before, right? The SAT score is a whole lot in the middle, a little bit on either end. How fast people can run 100 meters. Whole lot in the middle, really fast, me, right? Grades, a whole lot in the middle, really good, me, right? So, and what we call that is we call that the normal distribution. Symmetric, normal. So we say this is, and this should be normal. I didn't do a very good job here. You need to get good. However you can get good at drawing the bell curve, do it, because you're going to draw a lot of these. This is normally related data. Now, what do we know about normally related data? The mean is right down the middle. Now, is it exactly normal? No, it's approximately normal, right? Right? Touchdown passes by quarterbacks in the NFL are approximately normal. The average, the mean, and the median are about the same. You got some who throw a whole bunch and some who don't throw hardly any, but there's a whole cluster, right? In fact, skill level of the NFL quarterbacks is pretty much a normal distribution, right? There's not a great difference between, say, number 3 and number 27. Numbers 1, 2, and 3 are really good, and 28, 29, and 30 are going to be looking for another job next year. But that whole group in the middle is about the same. This is what's called normally related data. Well, here's what's kind of cool about normally related data. And this is the whole idea behind these topics in your introductory statistics and probability courses. You got your mean, and basically it doesn't matter whether we're talking about shoe sizes, SAT scores, or grades on the geometry test. If they're normally distributed, this is their distribution. From about -3 standard deviations to 3 standard deviations is almost 100% of your data. So if someone is 4 standard deviations above the mean or 5 standard deviations above the mean, they are way, way out there. They're almost outside of the data, okay? We call this curve, right, the normal distribution curve, 100% of the data is inside here. So the area in this curve, the area inside of the curve equals 100% of the data. And this is kind of an important point, and I'm going to kind of belabor this just a second. Because the calculations really aren't that hard once we start doing them, but I think the understanding is important, okay? Inside here, right, This is 100% of the data. This is where the percentiles come from. So, for example, what percentile would the mean be? It's a rhetorical question. Think about that for a second. What percent? Now, remember, percentile is the number that has that percentage of the data below it. So what percent of the data, just think to yourself, would be below the mean in a normally related data? If you're thinking 50%, you'd be correct. Okay? How about the first quartile? Would you be thinking 25% below that? How about the third quartile? Would you be thinking 75% below the third quartile? If you did, you'd be correct. And so our job for the next 2 weeks or so, and then certainly throughout inferential statistics, is going to be dealing with finding the various area under this curve. And and we know some of it already because we can standardize values. Here's the mean. Check this out. The mean is 0 standard deviations away from the mean. Here's 1 standard deviation. This is 34% of the data. It doesn't matter whether you're talking about SAT scores or shoe sizes. If you tell me the data is approximately normal, boom, I know this. Symmetric, here's another 34. 68% of the data, plus or minus 1 standard deviation. Now I know that 95% of the data is plus or minus 2 standard deviations. Maybe some of you have heard this before. Okay, so that's what? 27. So that's another 13.5%.
Is this for every curve?
Every curve.
Okay.
Every curve. As soon as you use the word normal, that's a loaded word. As soon as you use that word, then all this comes into play. And I'll show you an example in just a second. And then 3, it's 99% of the data. So we know this is another 2% here and another 2% here.
What's in between 34 and 2?
13.5, right? Because I have to get to 27. 13.5, 13.5, sorry. This diagram, by the way, is on your page under the document called 68, 95, 98.7 rule. Okay, so, and then this is 98. This is approximately 99%. So this is what we're saying here. So what does that mean for us, and how does that work? Pick a data set. If it's normally distributed, this is how it's going to work. Now, we're also going to learn how to do 1.5 standard deviations and 0.7 standard deviations, but let's look at 1, 2, and 3 for now. So here's 1, -1, -3, 0, 1, 2, 3. All right, so let's say we've got an SAT score. This is the most common one. All SATs have a mean of 100, a mean of 1,000, standard deviation of 100. So let's say you have an X of 1,200. How did you do? Well, first thing we do is we say, okay, my Z-score is 1,200 minus 1,000 over 100. So my Z-score is 2. Well, what percent area is to the left of 2? Well, let's see. It's 50 plus 34, 84, plus 13.5. So you're like the 97.5 percentile, right? So we're going to say you're the 97th percentile. Why? Because 97% of the scores are below 1200. What if you were 900? And I'll pause here in a moment, or you can pause the video anytime you want and calculate this stuff on your own. 900 minus 1,000 over 100. So now notice a difference here. I'm negative. Why? Because that would be one standard deviation below the mean. So there's 900 doesn't mean anything by itself. It only means something when it's associated with a mean and a standard deviation to get us to -1, right? What's the area to the left of -1? I go to -1, 13.5, 2, and maybe like a 0.5% down here. So you're at about the 15th or 16th percentile, approximately. Now, we have our computers and calculators will do this exactly, right? So this isn't 68, it's actually like 68.4 or something. But just for our pea brains, we do 68, 95, 99. It sort of helps us keep that in straight. Okay, so this is the idea here.
Wait,
Right.
I have a question.
Yep, so hold on just a second. So this is the idea. If you use the word normal, you're telling me that your data falls into that distribution. Now, if your data doesn't fall into that distribution, forget all this. But so much data does, and this is why we focus the entire chapter of the text on this. You know automatically that 68% is within one standard deviation, 95.2, 99.3, and in fact, you can calculate the percentiles based on those standard deviations. Now, are there other standard deviations? Sure. What if you got an 1150? And we'll talk about how to do that in the future. But this is the basic idea. 100% of the data is under the curve. Our job is to find out what percent is either to the left or the right of the Z score.